Diffusion models for multi-modal generative modeling. This paper focuses on generating synthetic data. In the paper, the authors try to extend the architecture of the denoising diffusion probabilistic model, or DDPM, to handle multimodal data. In this type of architecture, we begin with real data and progressively add a small amount of Gaussian noise at each time step by sampling from a distribution where the mean moves towards 0 and the variance approaches 1, resulting in a standard normal distribution at the final step. Here, beta t is a small positive value between 0 and 1 that increases gradually over time. And in the reverse or denoising process, we try to reconstruct the original data by incrementally removing the noise. We train a model that predicts both the mean and variance of the distribution. To train this model, DDPM uses a loss function based on the variational lower bound or elbow. The first term here encourages the final distribution to closely match a standard Gaussian, and by using the second term, we are simply comparing the distributions in the reverse process and in the forward process. Since the noise added in the forward process is known, this acts as our ground truth data, and we are trying to match these two distributions. Here is the idea. Instead of relying on a single data modality, which is common in generative tasks, such as working only with texts, or only with images, the idea is to combine information from multiple data types. The diagram illustrates the proposed architecture. On the left side, the process begins with data from different modalities, each residing in its own domain. And using modality-specific encoders, this heterogeneous data is mapped into a shared diffusion space through a process called forward aggregation. Then, similar to the standard DDPM, forward noising is applied to transform the data into pure noise. And finally, the reverse denoising process tries to reconstruct the original data using modality-specific decoder heads. And this way, we are able to compute task-specific losses. The authors introduced several practical multitask generative scenarios in their experiments, and I think that these examples help clarify the core idea of the paper. The first scenario, image transition, where the model tries to generate both an image and its corresponding segmentation mask simultaneously. In the second scenario, mask image training, the model learns to recover masked parts of an image while also learning to generate images from scratch. In the third case, the model generates both an image and its class label as shown here. And finally, in joint image representation generation, the model produces an image and a corresponding representation. I think that it's very interesting, especially in medical applications. For example, we can train a model on MRI scans paired with doctor's reports, and after training, the model can potentially generate new medical images along with coherent textual descriptions or even diagnostic notes. Here is the generalized form of elbow to train the empty diffusion model. L0 measures how close the final noisy latent ZT is to a standard Gaussian. By using L1, we are simply comparing the output of our model with our ground truth noise. L2 compares the true data distribution with the decoder's output from ZT for each specific data modality. And finally, L3 is the final reconstruction of the clean latent Z0 from the nearly clean Z1. This helps improve final sample quality. To train the model, we need explicit forms of these distributions. And to derive this, we begin by defining the forward transition probability or distribution as part of the forward process. This distribution is modeled as a Gaussian, where the mean aggregates information from all task modalities. Here xi represents a specific data type, ei the corresponding encoder, and the encoded modalities are combined using a weighted sum, and by incorporating the previous state, we are able to define this distribution, and by a change of parameter, we can derive the simplified version. These are the derived expressions necessary to use elbow. And in the reverse process, we need to define two sets of distributions: how to reconstruct the previous state given zt, and how to reconstruct each data modality given zt. But here, instead of directly predicting the mean and covariance, they used a unit architecture to predict the intrinsic noise added at each step in the forward process. We can then subtract this noise to recover the previous state. And here, xi and zt can live in different spaces. In that case, we need a data-specific decoder to map from the latent space back to the modality data space. This also has different forms depending on the data types. For example, for categorical modality data, this takes the form of cross entropy, and for continuous data, we have MSE loss. This diagram illustrates the encoders and decoders architecture. To simplify, the encoders do not introduce extra trainable parameters, and we are three different options. If the modality data space matches the diffusion space, for example, if we have images and their corresponding semantic segmentations, a simple identity mapping is used. If the spaces differ, a pre-trained generator is used, or the unit backbone is shared between the encoder and the decoder. To train the model, the previously presented elbow is simplified. For instance, L0 is independent of theta, so we can ignore it. And by substituting specific distributions into elbow and adopting the simple loss idea, we have the simplified form for loss. Here are some results. In the first experiment, the authors introduced masked image training inspired by BERT in NLP, where the images are randomly masked by setting small patches to 0, and the model is trained not to generate images from noise, but also to recover masked parts of images without altering the visible areas. And as shown in this table, the model achieved a very low LPIPS score, indicating that restored images are highly similar to the originals, and outperforming models like SDEdit. And this plot shows an interesting idea. Instead of using traditional classification, they perform conditional generation using samples from the validation set, and they produced synthetic images and labels, but they only keep the labels, and as you can see, the results are competitive. Here, for the first row, you can see the different setups for experiments. Randomly, patches of images were extracted and set to 0. In the second row, half of the image was masked, and the train is asked to produce 2 samples. And at the third row, all the images masked, so we have an image generation.